Our reality might be a cosmic illusion. Albert Einstein once noted that the most incomprehensible thing about the universe is that it is comprehensible. Today, that comprehension is being stretched to its absolute limits. This exploration will guide you through the 20 theoretical models, actively reshaping our understanding of space and time. By the end, you will see the fabric of reality in a completely new way. What if space is woven from tiny, vibrating strings? Could our three-dimensional world be a hologram projected from a two-dimensional surface? We will move beyond Einstein's relativity into realms of multiple dimensions and quantum foam, examining ideas that challenge our fundamental experience of existence and hint at technologies of the distant future. Each model is a crucial piece in the grand puzzle, from the well-known to the wildly speculative. What single question about the universe keeps you awake at night? That bedrock, the stage upon which our entire cosmic drama unfolds, is not a fixed and rigid thing. For centuries, the universe was thought to operate on a simple, absolute clockwork. Sir Isaac Newton envisioned space as a vast, empty container and time as a universal river flowing at the same steady rate for everyone, everywhere. This was a powerful and intuitive picture, one that explained the fall of an apple and the orbit of the moon with stunning accuracy. It framed reality as a grand, predictable machine. But then came Albert Einstein, and with him a profound and beautiful upheaval. His theory of general relativity tore down that absolute stage. It proposed that space and time are not separate entities but woven together into a single, flexible fabric called spacetime. Think of it not as a static backdrop, but as a dynamic, living canvas. In this new vision, mass and energy do not merely sit within spacetime, they actively shape it. A massive object like our Sun creates a curvature in this fabric, a gravitational well. Planets like Earth do not orbit because of some mysterious, invisible force. They simply follow the natural curves and contours of the warped spacetime around the Sun. Matter tells spacetime how to curve, and spacetime tells matter how to move. This was the elegant dance of general relativity, a theory so successful it predicted the bending of starlight and the existence of black holes. Yet, for all its grandeur in describing the cosmos, this theory harbors a deep and fundamental conflict. When we peer into the heart of matter, into the realm of the impossibly small, a different set of rules takes over, the bizarre and probabilistic laws of quantum mechanics. Here, particles can be in two places at once, information seems to teleport, and empty space seethes with temporary particles popping in and out of existence. This quantum world is a realm of chance and connection, governed by forces like electromagnetism and the strong nuclear force. And here lies the great dilemma, the central mystery driving modern physics. Our two most successful descriptions of reality, general relativity and quantum mechanics, are spectacularly successful in their own domains, but they are written in completely different languages. They are fundamentally, mathematically incompatible. General relativity paints a smooth, continuous fabric of spacetime, while quantum mechanics insists that at the tiniest scales, everything is grainy and discontinuous. Attempting to combine them, to describe the intense gravity of a black hole's singularity or the first moments of the Big Bang with quantum rules, leads to nonsensical answers, to equations that explode into infinity. This is not a minor technical issue, it is a screaming contradiction at the very heart of our understanding. For nearly a century, this conflict has stood as the greatest unsolved problem in theoretical physics. A silent war between the rules of the very large and the rules of the very small. This is why the models we are about to explore are not merely academic curiosities. They are necessary leaps of imagination, bold attempts to build a new framework that can contain both worlds. They are the quest for a single, unified theory of everything, a set of principles that would seamlessly describe the gravity that shapes galaxies and the quantum flutter that powers atoms. The journey to resolve this conflict begins with a theory that proposed a radical solution, one where the fundamental ingredients of the universe are not point-like particles, but tiny, vibrating strings. Into this cosmic conflict steps a theory of profound elegance and ambition. String theory proposes a breathtakingly simple answer to the question of what everything is made of. Forget the idea of fundamental particles as infinitesimal points. Instead, picture the universe's most basic ingredients as unimaginably small, vibrating loops or strands of energy. These are the strings. Their size is almost impossible to grasp, trillions of times smaller than the nucleus of an atom. But here is the beautiful part: the vibration of each string determines its identity. A string vibrating at one frequency might be an electron, the building block of electricity. A string vibrating at a different frequency becomes a quark, the heart of a proton. And crucially, one specific vibration would correspond to the graviton, the theoretical particle that carries the force of gravity. In this single, musical framework, the force that shapes galaxies and the particles that build atoms are unified, all born from the same vibrating essence. It is as if the universe is not built from inert Lego bricks, but from an eternal symphony, with each fundamental particle a unique note played on a cosmic instrument. For this symphony to work mathematically, however, the stage itself must be far grander than we perceive. String theory demands extra dimensions of space. We are familiar with three: up and down, left and right, forward and back. But this theory suggests there are 6 or 7 additional spatial dimensions, all curled up into intricate, tiny shapes at every single point in our familiar three-dimensional world. Think of a garden hose seen from a great distance. It looks like a simple one-dimensional line, but if you could shrink yourself to the size of an ant and crawl onto it, you would discover it has a second dimension, its circular circumference, curled up so tightly it was invisible from afar. Our entire reality could be like that hose, with hidden, compact dimensions woven into the fabric of space itself. Over decades, researchers developed several versions of string theory, each with its own mathematical structure. Then came a powerful insight known as M-theory, which proposed that these different versions were all facets of a single, deeper theory existing in 11 dimensions. In this view, our entire universe, with all its stars and galaxies, might be a vast three-dimensional membrane or brain floating within a higher dimensional space. This idea opens doors to radical possibilities, like gravity being a weaker force because it can leak into these extra dimensions, or other entire universes existing on separate branes entirely parallel to our own. Yet, for all its mathematical beauty and unifying power, string theory exists in a realm of profound challenge. The energy scales required to directly observe a string or probe the extra dimensions are far beyond anything our particle colliders can ever hope to achieve. This makes the theory, at least for now, notoriously difficult to test through experiment. Some critics argue it has drifted from physics into the domain of pure philosophy. But its defenders see it differently. They argue that by providing a consistent quantum description of gravity, it points the way forward when all other paths have failed. It forces us to think in radically new ways about what reality could be, pushing the very boundaries of human imagination. Whether it is the final answer or a magnificent stepping stone, string theory compels us to listen for the music that might be woven into the silent fabric of the cosmos. But what if the answer to the cosmic conflict lies not in adding more dimensions, but in reimagining the very fabric of the stage? While string theory builds an elaborate new symphony hall, a rival model takes the existing stage of spacetime and examines its fundamental grain. This is loop quantum gravity, and its vision is starkly beautiful in its simplicity. It asks a direct and revolutionary question. What if spacetime is not a smooth, continuous fabric, as Einstein described, but is instead woven from tiny, indivisible threads? In this model, the smooth continuum shatters. At the unimaginably small Planck scale, a distance so minute it defies ordinary comprehension, space itself becomes granular. Picture it not as a smooth sheet of glass, but as a vast, dynamic network of interconnected loops, a spinning mesh of reality. These loops, and the points where they intersect, form the absolute bedrock of existence. There is no smaller than this network, no empty space between the threads. This is where geometry itself becomes quantum. In loop quantum gravity, the familiar dimensions of space emerge from the connections within this network, much like the smooth image on a television screen emerges from countless tiny pixels. This pixelated vision of reality carries profound consequences, especially for the most extreme places in the cosmos. It directly challenges the terrifying infinities predicted by general relativity. Take the center of a black hole. Einstein's equations suggest all its mass is crushed into a point of infinite density called a singularity, a place where the laws of physics break down completely. But in the loop quantum view, spacetime cannot be compressed beyond its smallest possible grain. The gravitational collapse would reach a maximum density and then perhaps rebound. This leads to one of the model's most breathtaking ideas, a new origin story for our universe. The Big Bang may not have been a singular beginning from nothing, but a big bounce. Our expanding cosmos could be the rebound from a previous universe that contracted under its own gravity, passing through a phase of immense but finite density before springing back into a new expansion. In this cyclical view, time itself may extend beyond our cosmic horizon, with each universe inheriting a quantum imprint from the one before. Similarly, the model suggests that what we perceive as the event horizon of a black hole might not be a one-way gate to oblivion, but a region of extreme quantum spacetime geometry, potentially leading to another region of the cosmos or even another universe entirely. Yet, for all its power in describing the quantum structure of space and gravity, loop quantum gravity faces its own steep challenges. Incorporating the other forces of nature, like electromagnetism and the nuclear forces, into this woven framework has proven incredibly difficult. The model gives us a stunning picture of the stage itself, but a complete play requires all the actors, the matter and energy that move upon it. This ongoing struggle highlights the immense difficulty of unification. Where string theory seeks harmony by adding dimensions, loop quantum gravity seeks it by dissecting the dimensions we have down to their last thread. One paints with a broad, elegant brush, the other with a precise, pixelated point. Both are monumental efforts to answer the same fundamental call, to hear the true music of a quantized universe. While strings weave and loops spin, another path to quantum gravity emerges from the cold logic of geometry and computation. This is the world of causal dynamical triangulations, a model that asks us to rebuild the universe piece by tiny piece like a cosmic puzzle. Forget smooth fabrics or vibrating threads for a moment. Here, the fundamental ingredients of reality are the simplest geometric shapes imaginable, tiny triangles and their higher dimensional cousins. The idea is disarmingly straightforward. To understand the quantum structure of spacetime, we simulate building it. Researchers start with a vast number of these tiny, identical building blocks, each representing a minuscule chunk of spacetime. They then connect them together, gluing their edges according to one non-negotiable rule, causality. Every connection must respect the flow of time, ensuring that cause always precedes effect. You cannot glue a block representing now to one representing yesterday in a way that creates a time travel paradox. This rule imposes order on the chaos of quantum possibility. When you let a powerful computer simulate this process, exploring every possible way these triangular blocks can be glued together under the causal rule, something remarkable happens. From a frothing, jumbled quantum soup of possibilities, a clear and stable structure dynamically crystallizes. The simulation doesn't just produce a random shape, it generates a smooth, four-dimensional universe that looks very much like our own. It is a universe that computes itself into existence from the bottom up. This computational approach provides profound insights into the very phases of spacetime. Just as water can exist as ice, liquid, or steam depending on temperature and pressure, this model suggests spacetime itself can undergo phase transitions. The chaotic quantum jumble represents one phase. The ordered, four-dimensional universe we live in represents another, and the parameters of the simulation, like the way the blocks are weighted, act like a cosmic dial, tuning the universe from one state to another. This framework even offers a tantalizing hint about one of cosmology's greatest mysteries, the cosmological constant. This is the mysterious energy causing the expansion of our universe to accelerate, often called dark energy. In the simulations of causal dynamical triangulations, the emergence of a large, smooth, four-dimensional spacetime naturally correlates with a very small, positive cosmological constant. It suggests that the accelerating expansion of our cosmos might not be a strange accident, but an inevitable feature of a universe that has settled into its most stable, classical phase from a quantum beginning. This model stands as a powerful testament to a different kind of thinking. It shows how our continuous, flowing experience of reality can be the large-scale consequence of countless discrete, digital-like steps. It is a universe built not from strings or loops, but from information and connection, computing its own geometry into being with every passing moment. From a universe built like a computational puzzle, we arrive at a model that questions the very nature of its dimensions. The holographic principle proposes a reality so counterintuitive it feels like science fiction, yet it is grounded in the cold, hard logic of black hole physics. It begins with a profound puzzle about information. According to quantum mechanics, information cannot be destroyed. But what happens to all the information about an object, every detail of its atoms and their states, when it falls into a black hole? Stephen Hawking showed that black holes slowly evaporate, radiating away their mass until they potentially vanish. This created the infamous black hole information paradox, a direct conflict between the rules of gravity and quantum theory. The resolution proposed by physicists like Leonard Susskind is radical. The information is not lost inside the black hole. It is not even stored within its three-dimensional volume. Instead, it is perfectly encoded like a cosmic blueprint on the black hole's two-dimensional surface, its event horizon. Every detail of the three-dimensional objects that fell in is painted onto this distant, flat boundary. This is the essence of the holographic principle. Just as a flat, two-dimensional holographic film can project a stunningly realistic three-dimensional image, our experience of a rich, three-dimensional cosmos could be a projection from a vast, two-dimensional information layer at the edge of the universe. It suggests that all the information needed to describe everything within a region of space, every star, every planet, every one of us, could be written on its surrounding surface. This is not just a metaphor, it has a concrete mathematical realization known as the AdS-CFT correspondence. This is a powerful duality, a kind of cosmic dictionary that links two seemingly different worlds. On one side, you have a special warped space containing gravity described by string theory. On the other side, you have a quantum field theory that lives on the boundary of that space, a theory that has no gravity at all, only particles and forces interacting on a flat surface. The dictionary states that these are two completely equivalent descriptions of the same reality, a complex gravitational event happening inside the warped space, like two black holes colliding, can be perfectly translated into the frenetic interactions of quantum particles on the boundary. They are the same story written in two different languages. This blurs the line between the world we experience and the information that describes it to an astonishing degree. It hints that our three-dimensional reality, with its gravity and matter, might be an emergent phenomenon, a grand illusion generated by quantum information processing on a distant, two-dimensional screen. The universe, in this view, is not fundamentally made of stuff in the way we imagine, but of relationships and information. It is a cosmic computation, and what we perceive as solidity and depth is its magnificent output. This informational view of reality naturally compels us to ask, if the universe is a kind of quantum computer, what is it processing, and what are the fundamental bits of its cosmic code? The bridge between information and geometry is not merely theoretical, it has a name. The fifth model, known as AR equals EPR, forges one of the most unexpected and elegant connections in all of physics. It links two ideas that once seemed to belong to entirely separate worlds. On one side is ER, the Einstein-Rosen bridge, the scientific name for a wormhole, a hypothetical tunnel through spacetime connecting two distant points. On the other is EPR, named for Einstein, Podolsky, and Rosen, who first highlighted the bizarre phenomenon of quantum entanglement. This conjecture boldly states they are two sides of the same coin. It proposes that when two particles become entangled, their mysterious quantum link is not some abstract, invisible force. It is physically embodied by a microscopic wormhole, a Planck-scale tunnel woven into the very geometry of spacetime. Picture two particles at opposite ends of the galaxy, forever linked by a secret geometric shortcut. This is not a tunnel you could travel through. It is far too small and unstable, but it is a real feature of the fabric of reality. This single idea revolutionizes everything. Quantum entanglement, which Einstein famously called spooky action at a distance, is transformed. It is no longer just a strange informational correlation. It becomes a literal geometric connection. The spookiness is given a physical home in the structure of the universe. This has breathtaking implications, especially for the black hole information paradox. Recall that the paradox asks what happens to information that falls into a black hole. The holographic principle suggested it gets encoded on the surface. AR equals EPR provides a stunning geometric mechanism for how that could work. Imagine two entangled black holes. The conjecture suggests they would be connected by a macroscopic, traversable wormhole, a kind of cosmic bridge. Information that falls into one black hole could, in principle, travel through this wormhole and emerge from the other, never being truly lost. The event horizon is not a final wall, but a gateway in a connected geometry. This offers a potential solution to the paradox by showing how information can be preserved through space-time connections we are only beginning to understand. But the implications reach even further, touching the very origin of spacetime itself. If every instance of quantum entanglement corresponds to a tiny wormhole, then the vast, complex web of entanglement that makes up the quantum vacuum could be stitching together the fabric of our reality. Spacetime may not be a fundamental stage, but an emergent tapestry woven into existence by countless threads of quantum connection. In this view, geometry is born from entanglement. The smooth, continuous space we experience is the large-scale result of an unimaginably dense network of microscopic quantum links. It suggests that to truly understand gravity and the cosmos, we must first understand the quantum relationships that potentially build it from the ground up. This model moves us from a universe of separate things to a universe of profound and fundamental connection, where the distance between objects may be an illusion shaped by the depth of their quantum ties. If geometry itself is born from entanglement, then what are the fundamental events that tangle in the first place? The sixth model offers a profoundly minimalist answer. Causal set theory proposes that beneath the smooth flow of spacetime, there is no fabric, no field, not even geometry. There is only a vast, sparse collection of events, like individual grains of cosmic sand. Each grain represents a fundamental happening, a point where something occurs in the most basic sense. What gives this scattered dust meaning is not proximity in space, but relationship in time. These events are partially ordered by a single, irreducible principle, causality. One event can precede another, influencing it, being its cause. This creates a vast cosmic network of before and after, a family tree of reality itself. From this minimalist starting point, everything we recognize must emerge. The smooth, four-dimensional continuum of spacetime in which we live is not fundamental. It is a large-scale approximation, a blurry classical picture that arises from the immense density of these causal connections. Think of a finely detailed photograph. Up close, you see it is made of countless individual pixels, each a discrete dot of color. But from a distance, those pixels blend seamlessly into a continuous image. In causal set theory, our experience of a flowing, dimensional universe is that distant view. The pixels are the causal events, and the image they create is spacetime. This framework gives time a truly privileged role. Time is not an illusion, it is the primary reality. The entire structure is built from sequences of cause and effect. This naturally incorporates the relentless forward march we experience, the arrow of time, as a fundamental feature of the universe's architecture. The model also makes a startlingly simple prediction about one of cosmology's greatest puzzles, the cosmological constant, the mysterious energy driving the acceleration of the universe's expansion. The value of this constant is incredibly small, yet non-zero. In causal set theory, this number might not be an arbitrary parameter, but a statistical feature. It could emerge naturally from the random, poison-like sprinkling of the fundamental events that make up the cosmos. It would be a cosmic accident, but one with a predictable probability, much like the specific pattern of raindrops on a window is random, yet the overall density of the shower is not. This represents a radically different philosophy. Where other theories add layers of complexity, causal set theory pares reality down to its barest bones, order and connection. Spacetime is not a thing, it is a history. It is the story of what caused what, written in the most basic language possible. This pushes us to a profound shift in perspective, where time is not something that flows within the universe, but the very substance from which the universe is woven. From this view of reality as pure causal history, we are compelled to ask, if time is so fundamental, could its flow be measured not by clocks, but by the processing of something even more basic? Gravity is the force we know best, the pull that grounds us to our world. But what if this most familiar of cosmic actors is not a fundamental player on the stage, but merely an effect, an illusion cast by something deeper? The seventh model, emergent gravity, makes this radical proposition. It suggests that gravity is not a basic force like electromagnetism, but something that emerges from the collective behavior of countless microscopic bits of information. Think of it like the concept of temperature. A single air molecule does not have a temperature. Temperature is a property that only makes sense when you consider the average motion of trillions upon trillions of molecules. In the same way, this model proposes that gravity is a statistical effect, a kind of cosmic temperature that arises from the underlying quantum information of the universe. The most prominent version of this idea comes from physicist Erik Verland and is called entropic gravity. It begins with a startling image. Picture a spherical surface surrounding a region of space like a bubble. This is not a physical screen, but a holographic screen, a boundary containing all the information about what is inside. Now, imagine placing a mass like a star near this screen. The presence of the mass displaces the information on the screen. It changes the arrangement of the microscopic bits that encode reality. according to the laws of thermodynamics, systems naturally tend toward disorder, a state of higher entropy. The displaced information wants to return to equilibrium, to a state of maximum disorder, and it is this natural tendency, this entropic push to restore balance, that we experience as the force of gravity. The mass does not pull, the information on the screen pushes. In this framework, the equations of Newtonian gravity and even Einstein's general relativity are not fundamental laws, but approximate descriptions that fall out of the deeper principles of thermodynamics and information theory. It is a breathtaking inversion of perspective. Gravity becomes a consequence of the universe's innate tendency toward disorder, a side effect of how information organizes itself on the cosmic scales. This reframing leads to one of the most provocative implications of the model, a new perspective on one of cosmology's greatest mysteries, dark matter. We observe galaxies spinning so fast that, according to our known laws of gravity, they should fly apart. The invisible mass we call dark matter was proposed to provide the extra gravity to hold them together. But emergent gravity offers a different explanation. It suggests that in the low acceleration environment at the outskirts of galaxies, the relationship between inertia and gravity changes. The apparent extra gravitational pull we attribute to dark matter might not be caused by unseen particles at all, but could be a modification of the laws of inertia itself, a natural consequence of how gravity emerges from the quantum information of empty space. It is as if the stage itself has properties we did not account for, creating effects we mistakenly assigned to hidden actors. While this model is highly speculative and faces significant mathematical and observational challenges, its power lies in its philosophical shift. It asks us to consider that the forces shaping the cosmos might not be elemental but collective, emerging from a deeper layer of reality where information is the only true currency. It suggests that the force that guides planets and binds galaxies is a grand and convincing illusion, one with profound depth, woven from the universe's relentless drive toward disorder. The idea that gravity could be a collective illusion leads us to a model where even the stage beneath that illusion is rewritten. Non-commutative geometry proposes a universe where the very notion of a pinpoint location dissolves into a kind of permanent, fundamental haze. In our everyday world, the order in which you do things often does not matter. You can walk to the kitchen and then open the fridge, or open the fridge and then walk to the kitchen, and the outcome is essentially the same. The operations commute, but in the quantum realm, this familiar logic breaks down. A cornerstone of quantum mechanics is the uncertainty principle, which tells us that certain pairs of properties, like a particle's position and its momentum, cannot be known with absolute precision at the same time. The more you pin down one, the more the other blurs. Non-commutative geometry takes this quantum fuzziness and applies it to the coordinates of spacetime itself. At the unimaginably small Planck scale, the very act of measuring position becomes problematic. The mathematics suggests that if you try to measure one spatial coordinate and then another, the result you get depends on the order in which you take the measurements. X followed by Y does not give the same result as Y followed by X. This non-commutativity means that the concept of a definite point in space, a zero-dimensional dot, ceases to exist. Space is not made of points, it is made of overlapping, fuzzy regions where here and there blend together in a fundamental way. To describe this blurred reality, the model turns to a branch of abstract mathematics that studies the properties of algebras, much like the algebra you learned in school but vastly more complex. In this framework, the smooth, continuous geometry of Einstein's spacetime is not the true reality. It is a large-scale, classical approximation that emerges from a deeper, quantum algebraic structure, much like the smooth curve of a hill emerges from the jagged shapes of countless individual stones. The profound power of this approach is its unifying vision. The great dream of physics is to describe all forces and all matter within a single geometric picture. Non-commutative geometry attempts this by proposing that the particles and forces of the Standard Model, the electrons, quarks, photons, and all the rest, are not separate entities placed upon the stage of spacetime. Instead, they are spectral properties like the distinct notes or harmonics of space itself. In this deeply mathematical yet profoundly physical vision, the force of electromagnetism, or the existence of an electron quark, is not something added to geometry. It is a direct expression of the geometry's intricate, non-commutative shape. Matter and force are literally woven from the same twisted, fuzzy fabric. This offers a potential path to reconcile the Standard Model with general relativity, not by adding extra dimensions or vibrating strings, but by radically redefining the geometry we already have. It suggests that if we could perceive the universe at its most fundamental level, we would not see a neat grid of points, but a shimmering, algebraic symphony where location is a melody and particles are its harmonies. It is a reminder that our classical intuition of a sharply defined, pointillist reality may be the grandest approximation of all. This fundamental fuzziness of location points toward a universe where light itself might be the primary architect. The ninth model, Twistor theory, pioneered by Roger Penrose, proposes a breathtaking inversion of our usual perspective. In our standard view, we imagine particles moving through a pre-existing spacetime, tracing out paths called world lines. Twistor theory turns this completely inside out. It suggests that spacetime points are not the fundamental building blocks. Instead, they are derived from more primitive, ethereal objects called twistors. What is a twistor? In its essence, it can be thought of as representing a light ray, a ray of zero-rest mass traveling forever through the cosmos, but it also encodes the ray's quantum spin. The entire theory is built upon the geometry of these light-like connections. In this framework, a point in our familiar four-dimensional spacetime is not a simple dot. It emerges as the intersection, the meeting place of a family of twistors. Spacetime is not the stage, it is the performance, a secondary construction that crystallizes from a deeper, more fundamental network of luminous relationships. This radical reformulation was not born from pure abstraction, but from a desire to simplify some of the most complex calculations in physics. When particles like protons collide at near-light speeds in giant accelerators, physicists must calculate the probability, or amplitude, of every possible outcome. The mathematics for these scattering amplitudes can be monstrously complicated in traditional spacetime, but when translated into the language of twistor space, these calculations often become startlingly simple and elegant. Patterns hidden in the old equations become vividly clear, revealing a profound underlying geometry to the dance of fundamental particles. This success hints that twistors may be tapping into something very deep about the fabric of reality. For quantum gravity, the theory offers a compelling vision of a pre-geometric reality. Before there is space and time as we know them, there is this web of twistor connections. The smooth, continuous spacetime of general relativity would then emerge as a kind of large-scale, classical approximation from this buzzing quantum network of light-like links. It is a universe built not from stuff in places, but from relationships between events, with the speed of light and quantum spin as the primary ingredients. This perspective invites us to see the cosmos in a profoundly different light. We are asked to consider that the solidity of objects and the certainty of locations are illusions born from a deeper, shimmering reality of connections. The universe becomes a vast, luminous tapestry where every thread is a fundamental question about where light can go and how quantum spins align. It is a perspective that dissolves the container and leaves only the content, a web of potentiality from which everything we experience condenses. This shift from container to connection makes us wonder if our entire cosmic history, the entire arrow of time from the Big Bang to today, could itself be an emergent story written in a timeless language. The shimmering tapestry of Twistors suggests a reality built from luminous connections, but what if those connections weave a fabric far vaster than a single cosmos? The 10th model, Eternal Inflation and the Multiverse, proposes that our entire universe, with all its galaxies and laws, is merely a single bubble in an infinite, ever-expanding cosmic froth. This idea emerges from our best theory of the universe's explosive first moments, cosmic inflation. Picture a field, the inflattened field, that permeated the newborn cosmos. Like a ball resting in a high valley, this field was in a state of high energy, a false vacuum. This energy caused space itself to expand at a staggering, exponential rate, smoothing and stretching the universe in a fraction of a second. In most regions, this field eventually rolled down the hill, settling into its true, low-energy vacuum state. That release of energy reheated the region, filling it with the hot plasma of the Big Bang and creating what we now call our observable universe. But according to the theory of eternal inflation, this process never truly ends everywhere. Due to quantum fluctuations, some regions of the inflating space never settle down. In those patches, the inflation field gets kicked back up the hill or remains stuck in its high-energy state. As a result, inflation continues eternally in the background, while countless pocket universes like ours continuously nucleate as bubbles in this ever-expanding quantum foam. Each of these bubble universes could have its own unique destiny, its own random set of physical constants and laws, determined by how its inflation field finally decayed. In one bubble, gravity might be repulsive. In another, electromagnetism could be 1,000 times stronger, preventing atoms from ever forming. This leads to the staggering concept of a multiverse, often described in levels. The first level is simply a consequence of an infinite, post-inflation universe, where regions so far apart they are forever beyond our horizon have different initial conditions. The second level is the one from eternal inflation, these separate bubble universes with potentially different laws. Then there is the quantum many-worlds interpretation, where every quantum possibility branches off into its own reality, a multiverse of potential histories. While this is a framework of breathtaking scale, it is also profoundly challenging to test. By definition, other bubble universes are causally disconnected from our own, their light and signals forever unable to reach us. Yet, if two bubbles collided in the distant past, that cosmic crash might have left a faint, statistical imprint on the cosmic microwave background, a target for future observatories. The model's most compelling philosophical contribution is its answer to the puzzle of fine-tuning. Why do the constants of nature, like the strength of gravity or the mass of the electron, seem so exquisitely balanced to allow for stars, planets, and life? In an infinite multiverse where every possible set of laws plays out somewhere, it is no surprise that we find ourselves in one of the rare, hospitable bubbles. We are not the purpose of the cosmos, but simply its fortunate inhabitants. This stretches our concepts of space and time to a meta-cosmic scale, where the totality of existence is an eternal, generative process beyond human comprehension. It suggests that the story of our universe is just one chapter in a library of realities so vast its catalogue can never be read. Yet within this infinite froth of possibilities lies a profound practical problem, the measure problem. How do we make any predictions at all if every conceivable universe exists somewhere? An 11th model offers a radical solution by turning our gaze inward, back to the only reality we can ever truly know. Causal patch cosmology declares that the vast, unobservable multiverse is not just distant, it is fundamentally irrelevant to physics. What matters is the causal patch, the finite region of space and time from which light has had time to reach a single observer since the dawn of their universe. This is your past light cone, the sum total of every event that could have possibly influenced you, everything outside this cone, no matter how grand or strange, exists in a state of permanent quantum uncertainty, as real as a dream you will never have. This framework applies a kind of cosmic humility, a principle of mediocrity. We are not at the center of the universe, but our perspective is the only valid center for constructing a theory of our reality. By restricting physics to this observable patch, the model attempts to tame the infinite possibilities of the multiverse. Instead of asking why our universe has its specific laws, we ask what laws are most likely to emerge within a typical causal patch like our own. This shifts the question from a cosmic lottery to a statistical prediction based on what a localized observer would most probably see. The implications are deeply philosophical. It suggests that global questions about the entirety of existence may be forever unanswerable, not because we lack the technology, but because they are fundamentally meaningless from within any single universe. Reality becomes observer-dependent in the most profound cosmological sense. Your causal patch and mine overlap enormously, which is why we share a consistent world, but in principle they are unique. This model merges the largest scales of cosmology with the core puzzles of quantum mechanics, where the observer has always played a crucial, puzzling role. It proposes that the universe as a whole can be treated with quantum rules, and what we call the classical cosmos is the result of decoherence within our particular causal horizon. The grand multiverse does not vanish in this view, but it recedes into a quantum haze, a backdrop of potentiality against which our sharp, classical reality crystallizes. It is a reminder that all science, and indeed all experience, is ultimately local, built from the light that has touched us and the events that have shaped our corner of eternity. But what if the observer at the heart of their causal patch faces an impossible contradiction? The 12th concept is not a tidy model, but a screaming paradox that has shaken the foundations of modern physics. The black hole firewall paradox is a crisis born from trying to reconcile our most cherished principles, and it suggests a terrifying fate for anyone crossing a black hole's threshold. The story begins with a thought experiment from physicists Olmary, Marolf, Pulczynski, and Sully, known as the AMPS argument. They took the three bedrock principles of modern physics and showed they cannot all be true at the same time. First, quantum mechanics demands unitarity, the rule that information is never destroyed. Second, Einstein's equivalence principle states that crossing the event horizon of a large black hole should be uneventful, a smooth passage with no dramatic local effects. And third, quantum field theory tells us that no information can escape from behind the horizon faster than light. The AMPS team demonstrated with chilling logic that you can only pick two. If information is preserved and nothing special happens at the horizon, then a subtle form of quantum entanglement must connect particles just inside and just outside the black hole. But this creates a problem called monogamy of entanglement, a quantum rule that says a particle cannot be fully entangled with two different partners. To save the principle of information conservation, the delicate entanglement must be severed, and the energy released from breaking that immense number of quantum links would manifest not as a gentle glow, but as a catastrophic wall of ultra-high energy radiation, a literal firewall of incalculable temperature, burning up any infalling observer the moment they reach the event horizon. This is the paradox. The smooth spacetime of general relativity and the information preservation of quantum mechanics are at war, and the battlefield is the black hole's point of no return. The implications are staggering. It means the equivalence principle, the very idea that free fall feels like floating in empty space, fails catastrophically at the quantum level. The event horizon is not a peaceful gateway, but a boundary of fundamental conflict, a place where the fabric of reality might be shredded by fire. This crisis has become one of the most fertile grounds for new ideas in theoretical physics, precisely because it forces us to abandon comfortable assumptions. To resolve it, researchers are exploring radical notions. One path suggests that the interior of a black hole is not a separate place, but is somehow encoded in the chaotic, scrambled quantum information on its horizon, a concept linked to quantum error correction. Another idea posits that the key is computational complexity, the idea that the quantum information inside a black hole becomes so deeply scrambled and complex that it effectively builds the geometry of the interior, and the firewall appears only if an outside observer attempts an impossible calculation to verify the entanglement. These are not just technical fixes, they are profound shifts in how we view the relationship between information and reality. The firewall paradox teaches us that our deepest crises are not endpoints but invitations. They are the universe's way of telling us our map is incomplete, forcing us to redraw it with bolder, stranger strokes. It underscores that the journey to understand space and time is not a calm walk through a finished garden, but a turbulent voyage into a storm of contradictions, where each paradox lights the way to a deeper truth. This paradox of firewalls and broken entanglement forces us to ask if our entire mathematical language for the universe is simply too cluttered. What if the bewildering complexity of particle collisions, with their billions of probabilistic pathways, is not the true reality, but just a messy shadow of something far more elegant? The 13th model offers a vision of breathtaking purity. The Amplituhedron is a geometric object of stunning simplicity, a multi-dimensional jewel whose volume directly gives the probability of outcomes in particle interactions. To grasp its power, consider the old way. When physicists calculate what happens when particles like gluons smash together, they use a tool invented by Richard Feynman, diagrams with loops and lines representing every possible way the event could unfold. The number of these diagrams explodes with complexity, leading to calculations that can fill thousands of pages with algebra. The Amplituhedron sweeps all that away. For certain theories, it replaces this mountain of labor with a single, sublime geometric question. What is the volume of this shape? The answer to that volume is the scattering amplitude, the fundamental probability the old methods struggled to compute. This is not just a neat trick, it is a revelation. The Amplituhedron was discovered in the context of a specific, highly symmetric quantum field theory, but its existence hints at something profound about all of physics. The object itself is defined in a space that has no direct concept of spacetime, no notion of cause and effect, and no distinction between past and future. Locality, the idea that particles interact at specific points in space, and unitarity, the conservation of probability, are not built into it. Yet, when you calculate its volume, these familiar, cherished principles of physics emerge automatically in the answer. This suggests that our experience of a world where things happen in specific places and where probabilities add up to 100% are not fundamental laws but consequences. They are properties that bubble up from a deeper, timeless, and spaceless geometric reality. It is as if we have been studying the shadows on a cave wall, meticulously cataloging their movements, and the Amplituhedron is the first glimpse of the beautiful, solid object casting those shadows. The shape itself seems to encode only positive geometric realities, naturally avoiding the negative probabilities and infinities that plague traditional calculations. This points toward a future formulation of physics where the laws are not differential equations in spacetime, but the inherent properties of perfect shapes in some abstract Platonic realm. Particles and their collisions would not be the primary story, they would be the derived plot, read from the geometry of an eternal, silent jewel. It compels us to consider that the universe may not be computed, but simply measured, its entire quantum history contained within the facets of a form we are only beginning to comprehend. From the timeless geometry of the Amplituhedron, we arrive at a model that seeks to restore a lost cosmic balance. Supersymmetry, often called SUSY, proposes a profound and elegant partnership at the heart of reality. It suggests that the two great families of particles in the universe are not separate clans, but mirror images of each other. On one side are the fermions, the particles of matter, like electrons and quarks, the stubborn building blocks that make up everything solid. On the other side are the bosons, the force carriers, like photons and gluons, the social messengers that transmit interactions. Supersymmetry posits that for every known fermion, there exists a superpartner boson, and for every known boson, a superpartner fermion. An electron would have a selectron, a photon would have a photino. This introduces a whole new shadow population of particles, a hidden symmetry woven into the quantum fields. This is not just about neatness, it solves critical problems. One of the biggest puzzles in physics is why the Higgs boson, the particle that gives others mass, is so relatively light. In the raw math of the Standard Model, quantum fluctuations should drive its mass to an impossibly high scale, unless something tames those wild calculations. The superpartners provided by SUSY naturally cancel out these problematic fluctuations, stabilizing the Higgs and the entire structure of particle masses we observe. Furthermore, the lightest of these superpartners, often neutral and weakly interacting, becomes a perfect candidate for the mysterious dark matter that holds galaxies together. It is a particle that naturally emerges from the math, waiting in the shadows of every atom. Supersymmetry is also the essential engine that makes string theory work, providing the mathematical consistency that allows strings to vibrate in 10 dimensions and include gravity within a quantum framework. At the unimaginably high energies of the early universe, this symmetry would have been perfect. Fermions and bosons were in perfect balance, and all the fundamental forces, gravity included, were unified into a single, sublime interaction. Our current universe, with its distinct forces and lopsided abundance of matter, is a frozen remnant. It exists in a broken symmetry state, like a liquid that has cooled into a crystal. The perfect, symmetric partnership shattered as the cosmos expanded and cooled, leaving us with the asymmetric world we inhabit and hiding the superpartners at energies we have yet to probe. This elegant idea, for all its mathematical beauty, faces a stark experimental challenge. Despite decades of searching with our most powerful particle colliders, no superpartner has ever been directly observed. Their predicted masses must be far higher than initially hoped, placing the perfect symmetry of the early universe frustratingly out of reach. Yet, the profound appeal of SUSY endures because it offers a vision of a universe that is fundamentally balanced, stable, and unified. It tells us that the apparent chaos and distinction we see is a low-energy illusion, a temporary forgetting of a more perfect, symmetric beginning where matter and force were two faces of the same cosmic coin. The perfect symmetry of supersymmetry rests on a profound assumption that the laws of physics treat space and time as a unified whole. But what if this sacred union is not a fundamental truth, but a cosmic convenience? The 15th model, Horava Lifshitz gravity, makes a shocking proposal to save quantum gravity by breaking the most cherished rule of relativity. It suggests that at the deepest, most energetic levels of reality, time and space are not equal partners. Time retains its universal, flowing nature, but space itself becomes grainy, acquiring a fractal-like structure. This is a direct violation of Lorentz invariance, the principle that the laws of physics look the same to all observers moving at constant speed, the very symmetry that wove space and time together in Einstein's theory. By introducing this radical asymmetry at high energies, the model tames the wild infinities that plague attempts to quantize gravity. Gravity becomes renormalizable, meaning its calculations yield sensible, finite answers, opening a clear mathematical path to a quantum theory. This pragmatic sacrifice of symmetry for solvability leads to startling new visions of cosmic extremes. In the searing heat of the early universe, this fundamental difference between time and space would have been starkly apparent. The model predicts a different phase of expansion, potentially eliminating the need for a separate period of cosmic inflation to explain the universe's smoothness. When applied to black holes, the equations suggest the terrifying singularity at their core might be replaced by a bounce, a region of maximum curvature where matter and spacetime rebound. Perhaps most intriguingly, the altered behavior of gravity in this framework could naturally produce the observed acceleration of the universe's expansion, offering an explanation that does not require the mysterious dark energy. It presents a universe where the seamless spacetime continuum we experience is an emergent illusion, a low-energy truce that settles over a more fundamental, fractured reality. In this view, the elegant dance of relativity is not the final law, but a beautiful approximation that emerges as the cosmic fire cools, hiding the stark, operational truth that built the stage itself. The smooth spacetime we experience may be a truce, but what if the flow of time itself is not a one-way river? The 16th model, the transactional interpretation of quantum mechanics, proposes a radical vision where the future reaches back to touch the present. In the standard quantum story, a particle exists as a spread-out wave of possibilities until it is observed, at which point it mysteriously collapses into a definite location. This moment of collapse has long been a profound puzzle. The transactional interpretation offers a physical mechanism, one that requires waves traveling in both directions through time. Picture a quantum event like an electron being emitted from a source. It sends out an alpha wave forward in time, exploring all possible paths to a detector. Crucially, the detector then sends a confirmation wave backward in time, echoing along the possible paths back to the source. When these forward and backward waves meet, they form a resonant handshake, a transaction that reinforces a single, specific history. This completed transaction is what we perceive as a real, definite event in the present. The electron was not a fuzzy cloud that suddenly snapped into place. It was a negotiation finalized across time. This framework elegantly explains the famous double-slit experiment without invoking conscious observers or mysterious collapses. The alpha wave goes through both slits, but a stable transaction, that resonant handshake, only forms for paths that create the interference pattern we observe. It is a dance of causality that is inherently time-symmetric, treating past and future as equal participants in creating the now. When we scale this idea up to cosmology, the implications become staggering. It suggests a universe that is fundamentally symmetric in time, with a Big Bang and a potential Big Crunch, or a state of maximum expansion, acting as two boundary conditions that handshake across the entirety of cosmic history. Our expanding universe, with its clear arrow of time from past to future, would be just one half of a grander, two-way transaction. This opens the door to retrocausality, not in a paradoxical, sci-fi sense, but as a subtle, foundational process where future events help select which past possibilities become solidified into reality. The present moment is not a moving knife edge between a fixed past and an open future. It is more like a standing wave, a stable pattern forged by continuous negotiation between what was and what will be. While this interpretation is philosophically controversial and difficult to test directly, it provides one of the most concrete physical pictures for quantum weirdness, transforming spooky action into a structured conversation across time. It reshapes our understanding of time's arrow at the most fundamental level, proposing that the flow we feel is the outcome of countless quantum handshakes, each one a tiny stitch sewing the fabric of reality from both temporal directions. If the present is built by such transactions, then perhaps spacetime itself emerges from a deeper network of these timeless negotiations, a cosmic marketplace where every event is a deal struck between the beginning and the end. This cosmic conversation across time leads us to a model where the universe itself forgets its own age. Roger Penrose's conformal cyclic cosmology proposes a breathtakingly elegant vision of eternity, a cosmos without beginning or end, only an endless series of cosmic resets. In this picture, our universe is not a one-time event, but a single eon in an infinite sequence. The model hinges on a profound transformation that occurs in the far, far future. As the universe expands toward an unimaginable emptiness, all matter eventually decays or is swallowed by evaporating black holes. What remains is an ocean of massless particles, like photons and gravitons, drifting in an ever-cooling void. In this state, something remarkable happens. The particles lose all sense of scale, without mass to give them a fixed size, and with spacetime stretched to near infinity, the universe becomes conformally invariant. This means its geometry has no absolute ruler, no way to distinguish a vast expanse from a tiny point. The entire, unimaginably vast and cold future of our eon becomes geometrically identical to the hot, dense, and tiny starting point of a new Big Bang. The end smoothly, seamlessly transforms into a new beginning without a crushing singularity or a moment of nothingness. It is a cosmic metamorphosis where the dying breath of one universe is the first gasp of the next. Penrose suggests we might even see the ghostly imprint of the previous eon in our own sky. He points to strange, circular patterns of slightly lower temperature in the cosmic microwave background, the afterglow of our own Big Bang. He interprets these as the gravitational shock waves from supermassive black hole collisions that occurred in the eon before ours, imprinted onto the very fabric of our newborn cosmos. If verified, these Hawking points would be a fossil from a universe that existed before time as we know it began. Philosophically, this model is a profound departure from the standard story of a single, definitive creation. It replaces a linear timeline with a cyclic one, but not a simple repetition. Information is lost in the conformal reset, so each new eon is born fresh, with its own unique arrangement of matter and energy, its own history waiting to unfold. There is no eternal recurrence of the same events, but an eternal return of the potential for existence itself. Time becomes a series of grand, breathing cycles, an infinite rhythm of expansion and renewal. It challenges our deepest notions of origin and destiny, suggesting that every ending is secretly a preface, and every beginning is an echo from a past we can never fully remember. The endless rhythm of cosmic cycles hints at a deeper, perhaps even digital heartbeat. 18. Digital physics and the computational universe. This is not a single theory, but a profound philosophical stance, a suite of models that asks us to consider reality as a kind of vast running program. Pioneered by visionary thinkers like Konrad Zuse and Edward Fredkin, the core idea is breathtaking in its simplicity. What if the universe is not just like a computer, but fundamentally is one? In this view, the smooth, continuous flow of space and time is an illusion, a high-resolution display emerging from a fundamental grid of discrete, finite pixels. Physical laws are not equations written in some abstract Platonic realm. They are the operating code, the algorithms that govern how each pixel updates based on the state of its neighbors. Spacetime itself becomes a dynamic computational lattice, a cosmic cellular automaton where every tick of the clock advances the state of the entire grid. This perspective finds echoes in more mainstream quantum gravity research. The causal sets we discussed, with their discrete events ordered by causality, fit naturally into a computational framework. Similarly, the spin networks of loop quantum gravity resemble a dynamic data structure being constantly rewritten. Digital physics takes this a step further, proposing that this isn't just an analogy, it's the literal truth. The implications ripple out to touch everything. It reframes the nature of reality itself. particles and forces are not primary. They are stable patterns, emergent phenomena that arise from the complex interactions of the underlying code, much like the rich ecosystems that emerge from the simple rules of a simulation game. This leads to inevitable questions about free will. Are our thoughts and choices merely the output of a deterministic algorithm running on the wetware of our brains, which themselves are patterns in the cosmic computation? Or could genuine novelty arise from the processing of inherently unpredictable information? Perhaps most famously, this worldview opens the door to the simulation hypothesis, the idea that our universe is a construct running on some unfathomably powerful computer in a base reality. While this often veers into metaphysics, the digital physics perspective gives it a grounded, scientific flavor. If the universe is inherently discrete and computable, then it is, in principle, simulatable. The question then shifts from if we are in a simulation to why the underlying reality would itself be computational. This brings us to the most profound invitation of this model. It asks us to consider whether the cosmos is not just described by mathematics, but is mathematics in action. Reality is not a stage where mathematical truths are performed. It is the performance itself, a cosmic computation unfolding in real time, where every interaction, from the collision of galaxies to the firing of a neuron, is an expression of a deeper logical process. It is a universe that doesn't just contain information, it is made of it. The cosmic computer runs its code, but what if its calculations are being nudged by forces from outside the screen? Our 19th model confronts us with a mystery at the very edge of the map, a phenomenon known as the dark flow. Astronomers studying the motion of hundreds of galaxy clusters made a startling discovery. These vast structures, each containing thousands of galaxies, were not moving in a perfectly random cosmic drift. Instead, they showed a faint but coherent stream, all flowing in the same direction at tremendous speed, as if being tugged by something immense beyond the edge of everything we can see. This motion cannot be explained by the known mass distribution of our observable universe. It suggests a gravitational pull originating from far beyond our cosmic horizon, from a region of space-time whose light has not had time to reach us since the beginning of the universe. One compelling explanation reaches back to the era of cosmic inflation. If our universe is just one bubble in a frothing multiverse, perhaps this dark flow is the imprint of a gravitational tide from a neighboring bubble universe, a cosmic structure that inflated alongside our own and left a permanent directional tug on everything within our pocket of reality. It is a ghostly handshake from a cosmos we can never directly observe, forever altering the trajectory of our own. Closer to home, another challenge to the standard model arises from within the cosmic fluid itself. Related theories propose an alternative driver for the universe's accelerating expansion, replacing the mysterious dark energy with a property known as bulk viscosity. Think of the early universe not as a perfect, frictionless gas, but as a thick, complex fluid. Bulk viscosity represents an internal friction, a kind of resistance to expansion that arises as the fluid's components interact and dissipate energy. In certain models, this dissipative pressure can become negative, effectively acting not as a brake but as an engine, driving the expansion to accelerate just as we observe. This offers a radically different narrative. The cosmos isn't being pushed apart by a mysterious dark energy permeating empty space. It is being driven by the intrinsic, dissipative properties of the cosmic medium itself, a relic of its own turbulent, high-energy birth. Both the dark flow and bulk viscosity models represent profound challenges to the clean, self-contained picture of the standard cosmological model. They force us to consider uncomfortable possibilities. That our universe's dynamics might not be entirely its own, influenced by external structures forever hidden from our view, or that we have misunderstood the fundamental thermodynamics of space-time, mistaking an internal friction for an exotic new energy. They are stark reminders that our map of space-time, for all its sophistication, still has edges labeled "Here be dragons." The data whispers of influences from beyond the horizon and complexities from within the fluid, suggesting that the final chapter on cosmic expansion is far from written. But even the most elegant cosmic code must face the ultimate judge, the universe itself. Our final model is not a grand theory of everything, but the essential bridge that connects our soaring imagination to the hard ground of reality. The phenomenological approach represents the critical, ground-level work of testing these grand ideas. It is a methodology, a philosophy of science in action, focused on developing simplified, parameterized frameworks to hunt for the faintest deviations from general relativity and the standard model in the data streaming in from across the cosmos. This is where rubber meets the road, or rather, where space-time meets the detector. Consider the relentless pursuit to test the inverse square law of gravity at sub-millimeter scales. For centuries, we have assumed gravity behaves the same way at every distance, but what if it changes at scales smaller than a hair's width? Exquisitely sensitive tabletop experiments use tiny, oscillating cantilevers or torsion balances to measure the gravitational pull between minuscule masses. They are listening for a whisper, a hint that gravity strengthens or weakens at microscopic distances, which could be a sign of extra dimensions curled up so tightly they only affect the universe at the smallest scales. Meanwhile, the cosmic messengers known as gravitational waves have opened an entirely new window. Every ripple from colliding black holes or neutron stars is a pristine signal carrying information about the nature of gravity itself. Scientists meticulously analyze these signals for subtle anomalies, for echoes that might suggest a quantum frothiness to spacetime, or for deviations in how the waves dissipate that could point toward extra dimensions leaking away gravitational energy. Even the first image of a black hole's shadow, that fiery ring of light around the abyss, is more than a portrait. Its precise size and shape are a direct test of spacetime geometry in the most extreme gravitational environment possible. Any minute distortion from the prediction of general relativity could be a fingerprint of quantum gravity effects at the event horizon's edge. This pragmatic, model-independent search is the quiet, persistent engine of discovery. It ensures our theoretical explorations, for all their breathtaking beauty, remain anchored in observation. It is a reminder that the universe holds the final answer, and our role is to ask it ever more precise questions, listening with ever more sensitive instruments for the reply that will guide us, at last, toward the model that truly describes our reality. 20 different windows into the cosmos, each offering a unique and startling vision of reality's foundation. When we stand back and view them together, a breathtaking pattern emerges from the apparent chaos. Whether it is vibrating strings, woven loops, holographic projections, or digital pixels, the most revolutionary message echoing across these models is a shared whisper: space-time itself is not the bedrock. It is not the starting point of existence, but a magnificent and convincing illusion that emerges from something deeper, something often described in the language of information, connection, and geometry. The stage we thought was permanent is actually the performance, a grand production arising from a hidden backstage of quantum relationships. This is the profound synthesis of a century's most daring thought, a collective intuition pointing toward a universe where being is secondary to becoming, where substance is secondary to structure. The path forward now hinges on a delicate and thrilling convergence. Theoretical elegance must meet experimental evidence. The future of this quest will be written by the next generation of cosmic listeners and particle hunters. Enormous gravitational wave observatories, both on Earth and in space, will catch the faintest ripples from the dawn of time, listening for echoes of quantum foam or the distinctive ring of exotic compact objects predicted by loop quantum gravity. More powerful particle colliders will push into higher energies, searching not just for supersymmetry, but for any subtle deviation from the standard model that could hint at extra dimensions or new symmetries. And vast astronomical surveys, mapping the distribution of galaxies and the cosmic microwave background with unprecedented precision, will scour the data for anomalies, for the imprint of a colliding bubble universe or the subtle fingerprints of emergent gravity on galactic scales. The ultimate theory of quantum gravity may not wear a single label. It is increasingly likely that the final answer will be a hybrid, a synthesis that borrows the profound geometric insights of one model, the computational framework of another, and the mathematical tools of a third. The universe has never been obliged to conform to the neat categories of human textbooks. This grand intellectual adventure, from the smooth spacetime of Einstein to the pixelated potentialities of today, serves as a powerful reminder. Our understanding of reality is not a finished monument, but a living, breathing process of discovery. It is perpetually evolving, driven by that most human of impulses, an insatiable curiosity to decode the deepest secrets whispered by the cosmos. Each paradox, each crisis, and each breathtaking new model is not a failure but a signpost, guiding us closer to a truth far stranger and more wonderful than we have yet dared to dream. The journey through these possibilities reveals a cosmos far stranger than our ancestors could have dreamed. We have walked a landscape where time can bounce, where space is woven from threads of information, and where our entire three-dimensional reality might be a shimmering projection from a distant two-dimensional screen. Each of these 20 models is more than an abstract equation. It is a testament to human courage, a leap of imagination taken to answer our oldest and most profound questions. What is the world made of? Where did it all begin? What is the true nature of time? These are not just puzzles for physicists. They are the very questions that define our place in the grand scheme of things. While the mathematics may seem distant, the pursuit of these ideas stretches the limits of our technology and our minds, laying the groundwork for breakthroughs we cannot yet foresee. Perhaps one day, an insight born from this theoretical frontier will unlock new forms of energy, new understandings of matter, or new ways to perceive the universe itself. The physicist John Archibald Wheeler offered a beautiful metaphor for this endless quest. He said we live on an island of knowledge surrounded by a vast sea of the unknown. And as our island grows, as we push its shores further out, the coastline of our ignorance grows longer too. Every answer reveals deeper, more beautiful questions. Let this exploration be a starting point for your own curiosity. Which of these visions of reality resonated most deeply with you? Was it the cosmic symphony of string theory, the pixelated geometry of loop quantum gravity, or the timeless cycles of conformal cosmology? Share your thoughts below, and if you are hungry for more journeys to the edge of understanding, subscribe for future deep dives into the mysteries of space and time. The greatest adventure lies not in having all the answers, but in the perpetual act of wondering. Keep questioning.